Okay, guys, so this unit here is unit 3. We're going to talk about the atom, how it was discovered, what makes it up, okay, and talk a little bit about the periodic table. Okay, so let's start off first with what are atoms. Well, atoms are the smallest unit of matter that has all the properties of a given element. Okay, the simplest atom can be one single proton. But most of the time, an atom is going to contain protons, neutrons, in the center of mass surrounded by electrons. So there's 3 particles that make up an atom: proton, neutron, electron. Protons are positively charged. They have a mass of approximately 1 AMU, or really exactly 1 AMU. That's really the definition of a proton, or the definition of an AMU, the weight of 1 proton, or the mass of 1 proton. The neutron is a particle with about a mass of 1 AMU. It's actually a little bit more than 1 AMU. It's kind of really a combination of proton and an electron smashed together, sort of, kind of. And they are 1 AMU, so a little bit bigger than that. And then electrons are negatively charged particles with a mass of 1 over 2,000 AMU, so very, 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 very small compared to a neutron or proton. Okay. Protons and neutrons are found in the center of the atom in the nucleus, and then electrons are found outside the nucleus, floating around. All right. Now, an atom is classified as an element depending on the number of protons. So the number of protons in the nucleus, that determines the name of the element. Every atom with 1 proton is called hydrogen. Every element with 2 protons is called helium, 3 lithium, 4 beryllium, 5 boron, 6 carbon, so on and so forth. Okay. Now the number of neutrons can change. If they change, we get an isotope. The number of electrons can change. If they change, we get an ion. But it doesn't change the name of the element. Okay. So the number of protons, that's what gives an element its name. Okay. Now, where do these things come from? Well, or how do we know that atoms are made up of these things? We had scientific study, and over many, 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 many years, thousands of years, these things were discovered. Okay, so we'll talk about Democritus, Dalton, Thomson, Rutherford, Bohr, and also we'll talk about Schrodinger and Heisenberg as well. So first of all, the name atom came from this guy named Democritus around 400 BC, and he came up with this term called atomos. So his idea was that atoms were the indivisible and indestructible parts of every substance. Every substance was made of a different type of atomos. He thought if you cut, so if you took like a piece of cheese and you cut it and you cut it and you cut it and you cut it and you cut it, just kept cutting it smaller and smaller and smaller and smaller until you couldn't cut it anymore. When you couldn't cut it anymore, that would be an atom. Okay. So that's where you got that term, atomos. Atomos means uncuttable. So uncuttable, unable to cut. Okay. This was more of a philosophical thought. He didn't really have any necessarily scientific backing to back this up, or experimentation to back this up. And at the time, really the accepted idea was that of Aristotle and Socrates and some other more famous philosophers, that everything was made of the 4 elements: earth, wind, air, and fire. So it wasn't really, I don't know if it was really, I don't really know for sure, but I don't believe it was widely accepted. But he did coin the term atomos. Okay. Really now the more modern atomic theory, and the more, this one was done through scientific experimentation, really, with hydrogen and oxygen, was John Dalton's atomic theory. Okay. And he came up with 4 parts, and really this was the beginning of the modern day atom. He said that all elements are composed of tiny indivisible particles called atoms. The second part was that atoms of the same element are identical, whereas atoms of different elements are different. And then the third part, atoms can combine physically or chemically in simple whole number ratios. And then finally, chemical reactions occur when atoms are separated, joined, or rearranged. Atoms of one element cannot become another through chemical reactions. Okay. So 2 of these held true, and 2 of these have been proven false. So the first 2, all elements are composed of tiny indivisible particles called atoms. That is no longer true. We know that atoms are made of protons, neutrons, and electrons. Okay, so they're not necessarily indivisible. You can break them apart. You can divide them. You can divide them further down. Okay. The second one also is not really true, because again, if you have an element, the number of protons stays the same, but we can change the number of electrons, we get an ion, or we can change the number of neutrons, we get an isotope, but they still are the same element. They still are the same element. They pretty much have the same chemical properties, regardless of how many neutrons or how many electrons they have. Well, not exactly electrons, they change their properties a little bit, but in general, their properties are the same. Okay, but number 3 and number 4 stay true. Atoms always combine in whole number ratios. You can't have half an atom combined with a half of another atom. Okay, and chemical reactions occur when atoms are separated, joined, or rearranged. And that is true as well. Okay, and you cannot change an element through a chemical reaction. It just doesn't happen. Okay, now J.J. Thomson was the one who discovered electrons in 1897. He was able to show that electrons existed by using this cathode ray tube. So basically, he was running electricity through a gas in a tube, and you can see the electrons glowing as they flow through the tube. And then he showed that they were negatively charged by putting a magnetic field or a magnet near it, and then it bent the electrons, the electron path. Bent the electron path. So he was able to discover electrons, and he came up with a model for the atom where you had these negatively charged particles floating or interdispersed through a positively charged mass, and he called it his plum pudding model. If you think about like bread pudding, often has little raisins kind of interspersed with that, or if you had like a chocolate chip muffin or a blueberry muffin, he thought that's what it looked like little particles interdispersed through a positive mass. Okay. Then we had Ernest Rutherford come along, and he proved that the atom was not like that. What it was instead was mostly empty space with a dense positive center, and he was able to show that through this gold foil experiment. So he took a piece of gold foil and he bombarded it or hit it with these alpha particles, or basically just helium atoms. He's throwing charged helium atoms at this gold foil, and he thought, well, if atoms are like Thomson said they are, then those particles should just bounce right back, because if it's a positive mass, then the particles will hit it and bounce right back. But what instead he saw was that actually most particles went straight through. Most particles weren't deflected or reflected back. Okay. A lot of particles went straight through. Some of them were slightly deflected. So what he thought was, oh wow, that's interesting. That atoms must be then mostly empty space. And as far as we're concerned today, we believe that atoms are 99% empty space. So we don't really know what's there. It's, as far as we're concerned, nothing. But we don't really know. So 99% of the atom is empty space. And then there's a dense positive center. Okay. So there's a dense positive center. He wasn't able to necessarily to find neutrons just yet. Someone actually else came along and discovered neutrons. But I think he had the inkling that, well, there is mass in the center. It doesn't really make sense if they're just protons, because the positive charge doesn't really add up to the total mass of it. So there must be something else there. But I don't believe he was able to discover neutrons just yet. Okay. So again, Ernest Rutherford found this dense positive center in the nucleus. Then Niels Bohr came along in 1913, and he found that electrons aren't just willy-nilly floating around the nucleus, outside the nucleus. They're actually organized they're organized in energy levels. Okay, he thought that they rotated around the nucleus like planets around the sun. Okay, that's not exactly true, but that's what he thought. Okay, he called it the planetary model. So he thought that electrons rotated around the nucleus like planets around the sun. And he discovered this, or he found this, because he noticed that elements always gave off certain wavelengths of energy. Every time an element, an atom of a certain element was excited with electricity or heat or something like that, and it always gave off the same wavelengths of energy. So they figured that these electrons were being excited, then they were relaxing, and every time they were always jumping between the same amount of energy. They were giving off the same amount of energy. Okay. And again, we're not really going to talk about this too much about the principle behind this, but he did this with a lot of math and checked it, and he was able to do the math for hydrogen, but when he got to helium, his calculations didn't quite work. So he was like, well, my theory's close, but there's something else going on here I don't quite understand just yet. Okay. And the other two guys that were able to figure it out were Heisenberg and Schrodinger. So they found that the electrons were not actually rotating around like planets. Instead, they were found in energy levels. The electrons kind of move pretty randomly. They move randomly. They don't just rotate. You can't actually figure out exactly how fast or where the electrons are at any given time. You kind of have to guess. You don't really know for sure. Okay. So instead of them floating or like going around like planets around the sun, they were just found in a given space. Okay, and they call it the electron cloud, where the space where electrons are likely to be found. Okay. And then finally, if we look at the periodic table, we can actually figure out the number of protons, neutrons, and electrons given these things here. So we have the atomic number on the top. The symbol is just a shorthand and for chemical equations. It's always started with a capital letter and ends with a lowercase letter. Okay, if you're one of those people that always writes capital letters, or always writes lowercase, you need to make sure that it always starts with a capital and then ends with lowercase letters. Okay, it's very, very important. And then you usually have the name and then the mass number. Now the mass number is the number of protons and neutrons in the nucleus. So add them together. Protons plus neutrons gives you the mass number. Okay. So if we're trying to find number of protons, it's always equal to atomic number. Super easy. Electrons equal number of protons in a neutral atom. That's all we're doing for the moment. Okay. We'll talk about ions another day. Okay. And then if we want to find the number of neutrons, we take the mass number and we subtract the atomic number, and we should get the number of neutrons. Okay. So all that information, use that to answer that worksheet. And then we'll talk more tomorrow. All right. Have a good day, everybody.